Tonight, we're going to ask one of the most ancient and most precisely stated questions in all of physics. What lies on the other side of the speed of light? Not what do we imagine lies there, not what science fiction has placed there, but what physics, the most carefully tested body of knowledge in human history, actually says about the question. The answer is more complicated, more interesting, and in several places more counterintuitive than either the popular dismissal that nothing can go faster than light or the popular hope that somehow the barrier will eventually be broken. The speed of light in vacuum is approximately 299,792,458 meters per second. It is not a speed that anything has been measured to exceed in vacuum, and the reasons it cannot be exceeded by any massive object or information-carrying signal are not merely technological limitations waiting to be overcome by better engineering. They are structural features of spacetime as physics currently understands it, embedded in the mathematics of special relativity in a way that does not permit negotiation. The light barrier is not a wall in the engineering sense. It is more like the statement that you cannot travel north from the North Pole. It describes a boundary in the structure of the thing itself rather than an obstacle imposed from outside. And yet the question of what lies past it is not simple to dismiss, because the universe already contains things that move faster than light and contains regions that light itself cannot reach. The expansion of the universe carries galaxies away from each other at speeds exceeding the speed of light for sufficiently distant pairs. Cosmic inflation in the universe's first moments expanded space at rates incomparably faster than light. Quantum entanglement produces correlations between particles that seem, at first encounter, to suggest some form of faster-than-light influence. The phase velocity of electromagnetic waves in certain media exceeds the speed of light. Hypothetical particles called tachyons would, if they existed, move exclusively faster than light and could never slow to it. The distinction between these different senses of faster than light, which of them carry information, which of them could in principle be used for communication or travel, which of them are genuine departures from the standard picture and which are features of the standard picture itself, is one of the most instructive exercises in precision thinking that physics offers. Getting it right requires understanding not just what the speed of light is, but what kind of thing it is, a property of spacetime geometry rather than a property of light specifically. By the end of tonight, you will understand what physics says about each of these faster-than-light phenomena, why some of them are genuine and some are apparent, what the most serious proposals for circumventing the light barrier actually require and what makes them difficult or impossible, and what the philosophical and physical implications are of living in a universe built around a specific, finite, unbreakable maximum speed. If this kind of careful, detailed, honest investigation of a question that sits at the boundary of known physics is what you're here for, subscribe and leave a like. It genuinely helps this channel reach more people who want the real version. Now, let us start with what the speed of light actually is. There is also something worth saying about the framing of the question itself. The phrase the light barrier implies something that exists as a barrier in the engineering sense, something that could perhaps be breached with sufficient force or cleverness. This framing is understandable given the historical precedent of the sound barrier, which was genuinely a barrier in the engineering sense, a regime of aerodynamic behavior that made high-speed flight very difficult but that was eventually overcome through the right aircraft design. The metaphor suggests that FTL travel might similarly be achievable once the right approach is found. The physics suggests this analogy is deeply misleading. The sound barrier was a collection of aerodynamic challenges that happened to cluster at a particular speed. The light barrier is a structural feature of spacetime itself. Overcoming it is not an engineering challenge in any familiar sense. If it can be overcome at all, it will require either the discovery of entirely new physics that modifies the structure of spacetime at levels not yet explored experimentally, or the creative use of existing physics in ways that circumvent the limit through geometry rather than brute force. Both possibilities are worth examining seriously, and tonight we will do exactly that. The speed of light, abbreviated c from the Latin celeritas meaning swiftness, is not primarily a property of light. This is one of the most important and least commonly understood facts in physics. Light travels at c because of what light is, a propagating disturbance in the electromagnetic field, and the electromagnetic field propagates at c. But the reason c is the relevant speed is not that it happens to match what we measure for photons in vacuum. It is that c is a feature of spacetime geometry itself, a conversion factor between space and time, the single parameter that makes them commensurable as aspects of a unified four-dimensional structure. This was made fully explicit in 1905 when Einstein published the special theory of relativity. The two postulates of the theory are that the laws of physics are the same in all inertial reference frames, and that the speed of light in vacuum is the same for all observers regardless of their relative motion. From these two postulates, The entire structure of special relativity follows by logic. But the second postulate can be read in a more fundamental way. It is not that light happens to travel at a constant speed. It is that there is a maximum speed built into the structure of spacetime, and light, being massless, naturally propagates at that maximum speed. This reframing matters because it clarifies what the light barrier actually is. It is not a speed that light happens to have and that massive objects cannot reach because they are somehow slower or less energetic. It is the speed at which anything that has no rest mass travels, and massive objects cannot reach it because the mathematical structure of spacetime makes infinite energy a prerequisite for any massive object to reach that speed. Light is not the thing that sets the limit. Light is the thing that naturally rides the limit because it has no rest mass to constrain it. The value of c in meters per second appears in the relationship between space and time measurements in the Lorentz transformations, in the relativistic energy-momentum relationship, and in the relationship between the electric and magnetic field constants of Maxwell's equations. Maxwell's equations were derived experimentally in the 19th century, and when their consequences were worked out, the speed of electromagnetic wave propagation came out to a specific value. The fact that this value matched measured values for the speed of light was the original evidence that light was an electromagnetic phenomenon. In SI units since 1983, the meter is defined in terms of c. 1 meter is the distance light travels in exactly 1/299th, 792, 458 seconds. This makes c exactly 299,792,458 meters per second by definition, and distance is measured operationally by timing light. The speed of light is therefore not something measured, it is something defined. The measurement question becomes instead how precisely we can measure the second, which is defined in terms of the frequency of cesium-133 transitions. The constancy of c is therefore deeply embedded in the operational foundations of modern measurement. The relationship between c and Maxwell's electromagnetic constants reveals something important about why c has the value it has in SI units. The magnetic permeability of free space, mu0, and the electric permittivity of free space, epsilon0, are the fundamental constants of the electromagnetic field. Maxwell showed that electromagnetic waves propagate at a speed equal to 1 divided by the square root of mu0 times epsilon0. The numerical values of these constants, measured experimentally in the 19th century, produce exactly c. This tells us that c is not an arbitrary number chosen by the universe, but emerges from the specific strengths of the electromagnetic force relative to the scale of distances defined by our unit system. In natural unit systems used by physicists, c is set equal to 1, making its value a consequence of how units are chosen rather than a fundamental input. In these systems, mass and energy have the same units, space and time have the same units, and the relationship E equals mc squared becomes simply E equals m. The naturalness of setting c to 1 in these unit systems reflects the fact that c is fundamentally a conversion factor between space and time, not a speed in the sense of an external constraint. The reason no massive object can reach the speed of light is captured precisely in the relativistic energy-momentum relation, one of the most important equations in physics. The total energy of a particle is equal to the square root of the sum of the square of its rest energy and the square of its momentum times c squared. For a particle at rest, this reduces to the famous E equals mc squared. For a moving particle, the total energy is always greater than the rest energy, and the excess is the kinetic energy of motion. The specific behavior as velocity increases is governed by the Lorentz factor, gamma, which equals 1 divided by the square root of 1 minus the square of velocity divided by the square of c. At low velocities, the Lorentz factor is essentially 1 and the particle's kinetic energy is well approximated by the classical formula, 1/2 mass times velocity squared. But as velocity approaches c, gamma increases without bound. At 90% of the speed of light, gamma is approximately 2.3. At 99%, it is approximately 7.1. At 99.9%, approximately 22.4. At 99.99%, approximately 70.7. What this means for the energy required is that as you try to push a massive particle closer to the speed of light, the energy required grows without limit. Each additional fraction of c requires more energy than all the energy added previously. There is no finite amount of energy that gets a massive particle all the way to c. The curve of required energy versus velocity goes to infinity exactly at c, never reaching it at any finite energy input. This is not a practical engineering difficulty. It is a mathematical certainty that follows from the structure of the Lorentz transformation. Particle accelerators demonstrate this effect directly. The Large Hadron Collider at CERN accelerates protons to approximately 99.9999991% of the speed of light, achieving a Lorentz factor of roughly 7,460. At this speed, the proton's kinetic energy is approximately 6.5 teraelectronvolts, over 7,000 times their rest mass energy. Adding more energy would push the Lorentz factor higher, but the speed would barely increase. At 7,460 times the rest mass energy, getting to 99.9999910% of C would require yet more energy. The approach to C is asymptotic. This asymptotic behavior is not a feature of any particular propulsion mechanism or any particular particle. It applies to every massive object universally. An electron, a proton, a person, a planet. All of them, if accelerated, see the same asymptotic approach to C, requiring infinite energy to actually reach it. The argument can also be approached from the perspective of momentum rather than energy. In special relativity, momentum is mass times velocity times the Lorentz factor. As velocity approaches c, the Lorentz factor goes to infinity, so the momentum also goes to infinity. The relationship between force and acceleration is that force equals the rate of change of momentum. If an infinite momentum must be achieved to reach c, and each incremental increase in momentum requires a force applied over a time interval, the total impulse needed to reach c is infinite. No finite force applied over any finite time interval, however large, can provide infinite impulse. This is another way of expressing the same fundamental constraint. The experimental precision with which this is confirmed at particle accelerators is extraordinary. The trajectory of particles in the magnetic fields of accelerators depends on their momentum, and the exact relationship between rigidity, the product of magnetic field and orbital radius, and velocity confirms the Lorentz momentum formula to better than 1 part in 10 to the 16th over a range of velocities from very low to above 99.9999% of c. There is no regime where a departure from the relativistic prediction has been observed, and the precision of the tests continues to improve with each generation of accelerators and detectors. As a massive object approaches the speed of light, the effects of special relativity become progressively more extreme, and understanding these effects is essential for understanding what the light barrier actually means experientially and physically. The effects are real. They are not perceptual illusions or measurement artifacts, but genuine features of spacetime that have been confirmed experimentally in numerous contexts. Time dilation increases with the Lorentz factor. A particle moving at 99.9% of the speed of light has a Lorentz factor of approximately 22.4, meaning its internal clock runs at roughly 4.5% of the rate of a stationary clock. Unstable particles created at high energies in cosmic ray interactions in the upper atmosphere travel at high Lorentz factors and survive long enough to reach Earth's surface, a journey that takes microseconds of their proper time but many times longer in the Earth's reference frame. This is a direct observation of time dilation at relativistic velocities. Length contraction is the companion effect. An object moving at high velocity is contracted in the direction of motion by the same Lorentz factor. At 99% of c, an object is contracted to approximately 14% of its rest length in the direction of motion. At the Lorentz factor of 7,460 achieved by LHC protons, the proton is contracted to approximately 0.013% of its rest diameter in the direction of travel. For the proton's own experience, it is the entire LHC ring of 27 kilometers that is contracted to approximately 3.6 meters. Relativistic aberration changes the apparent directions of objects. As a spacecraft accelerates to near C, the light from stars ahead of it is blue-shifted and apparently concentrated toward the forward direction. A traveler moving at 99% of C would see most of the starlight concentrated within a forward cone of about 8 degrees, leaving the remaining 352 degrees of sky nearly dark. The stars behind would be dramatically red-shifted and essentially invisible, while stars ahead would be blue-shifted into the ultraviolet and beyond. Relativistic Doppler effect shifts all frequencies of electromagnetic radiation. For an observer moving toward a source at 99% of C, the received frequency is approximately 14 times the emitted frequency. Radio waves become visible light. Visible light becomes X-rays. The energy of individual photons scales the same way. A 1 electron-volt photon becomes a 14 electron-volt photon. As velocity approaches c, all of these effects approach their extreme limits simultaneously. Time dilation approaches infinity, meaning proper time nearly stops. Length contraction approaches zero in the direction of motion. relativistic mass approaches infinity, as does the required energy. The approach to c is a limit in the full mathematical sense, a value that all of these quantities approach but that can never be reached. The visual experience of near-light speed travel, as computed from the equations of relativistic optics and aberration, was first simulated systematically in the late 20th century and produces effects that have no intuitive connection to ordinary visual experience. In addition to the concentration of starlight and frequency shifting already described, there is a phenomenon called Penrose-Terrell rotation in which fast-moving spheres appear rotated rather than flattened, despite their actual length contraction. The optical effect of light travel time from different parts of the object to the observer's eye exactly cancels the length contraction effect for objects moving transversely, producing an apparent rotation of the object. Direct length contraction can only be measured precisely by simultaneously marking both ends of the object in the observer's rest frame, not by photographing it. For a traveler approaching C, the cosmic microwave background radiation, normally a nearly uniform microwave glow at about 2.725 Kelvin permeating the sky in all directions, would be dramatically blue-shifted ahead of them. At 99% of C, the CMB ahead would be shifted into the infrared and visible range. At 99.9999% of C, the CMB ahead would be in the gamma-ray range, delivering significant radiation doses. Traveling at extreme fractions of C through the actual interstellar medium would therefore involve significant radiation hazards from both the blue-shifted CMB and from interstellar gas and dust, which at relativistic speeds present as a beam of highly energetic particles. The question of why the universe has a maximum speed is genuinely deep and does not have a complete answer that goes beyond pointing at the mathematical structure of special relativity. But several perspectives illuminate why a finite maximum speed is not an arbitrary restriction but seems to be connected to the coherence of the universe's causal structure. Causality, the principle that causes precede their effects, is intimately connected to the finite speed of light. In the spacetime geometry of special relativity, events are connected by relationships called spacetime intervals. Two events with a time-like interval, where the time separation is larger than the space separation divided by c, can be causally related. A signal moving at or below the speed of light can travel from one to the other. Two events with a space-like interval, where the space separation exceeds the time separation time c, cannot be causally related. No signal at or below c can travel between them. This distinction between time-like and space-like intervals is an invariant feature of spacetime. It is the same in every reference frame. Whether two events are causally connectable does not depend on who is observing them. This invariance is what makes causality a robust principle rather than a frame-dependent one. If signals could travel faster than light, there would be reference frames in which those signals traveled backward in time, violating causality. The light barrier is therefore not just a speed limit but a causal horizon, a boundary that separates what can and cannot influence what. A universe without a maximum speed would face serious problems with its causal structure. The entire architecture of how events relate to each other, which events can influence which future events, would be frame-dependent and inconsistent across observers. A maximum speed, specifically c, is what allows a consistent, observer-independent causal structure to exist. The universe built its speed limit to protect its own logical consistency. There is a deeper perspective from quantum field theory. The requirement that physical measurements in one region of space cannot affect measurements in a space-like separated region, called microcausality or local commutativity, is built into the mathematical structure of relativistic quantum fields. Fields at space-like separated events must have commuting operators. This is not an empirical constraint added to the theory. It is a structural requirement for the theory to be consistent with the relativistic causal structure. Violate the speed limit and microcausality breaks down with it. The principle of locality, that physical influences propagate continuously through space rather than instantaneously between distant points, is the deeper requirement that the speed limit enforces. A universe with infinite propagation speed would have to specify physical states instantaneously across all space simultaneously, requiring a preferred reference frame against which simultaneity is defined. Special relativity demonstrates that no such preferred frame exists. All inertial frames are equivalent, and simultaneity is relative. The maximum propagation speed c is what makes this consistency possible. Defining causality through c provides an invariant criterion for causal ordering that is the same in all reference frames. This connection between the maximum speed and the lack of a preferred reference frame is not coincidental. The Lorentz invariance of physics, the fact that the laws look the same in all inertial frames, requires a specific relationship between space and time that is precisely characterized by the parameter c. If c were different, the specific numerical value of the speed limit would change, but the qualitative relationship, a maximum propagation speed whose square root of 1 minus v squared over c squared factor enters all relativistic formulas, would remain. The value of c is an empirical fact. The existence of such a limit seems to be a theoretical necessity of any consistent relativistic spacetime. There is a mathematical way to state this connection between c and causal structure that is particularly illuminating. In Minkowski spacetime, the metric, the mathematical object that measures spacetime intervals, has a specific signature: 3 positive spatial dimensions and 1 negative temporal dimension. The negative sign for time is what distinguishes spacetime from ordinary 4-dimensional Euclidean space, and c is the conversion factor between the spatial and temporal dimensions. The light cone, the set of all events that can be causally connected to a given event, has c as its defining parameter. Change c and you change the shape of the light cone, which changes which events can influence which other events, which changes the entire causal architecture of the universe. The specific value of c sets the aspect ratio of the light cone and therefore the specific causal geometry within which all physical processes take place. Despite the impossibility of massive particles or information-carrying signals exceeding the speed of light, the universe already contains phenomena that are genuinely, measurably faster than c. These are not violations of special relativity. They are features of the theory itself, consequences of the geometry of spacetime and the nature of the physical quantities involved. Understanding them precisely is one of the best ways to understand what the light barrier actually prohibits and what it allows. The expansion of the universe is the most dramatic example. Galaxies beyond a certain distance, called the Hubble radius, are receding from Earth faster than the speed of light. The current Hubble radius is approximately 14.4 billion light-years. Galaxies beyond this distance are moving away from us faster than c, and the distance continues to grow. This does not violate special relativity because the galaxies are not moving through space faster than light. The space itself is expanding, and the recessional velocities arise from this expansion, not from any intrinsic motion of the galaxies through their local spacetime. Special relativity applies locally. It does not constrain the rate of expansion of space itself. The scissors metaphor illustrates another class of FTL phenomena. If you have a pair of scissors with very long blades and you close them rapidly, the point where the blades intersect moves along the blades. If the blades are long enough and you close them fast enough, this intersection point can move faster than light. The point is not a physical object. It is a geometric feature, the location of an intersection. No mass or energy is transported along the blades faster than light. The intersection is simply a mathematical consequence of the geometry. This is genuine faster-than-light motion of a point that is not a material object and cannot carry information. Reflections and shadows can similarly move faster than light. If a distant wall is illuminated by a rotating spotlight, the spot of light on the wall can move faster than c if the wall is far enough away and the rotation is fast enough. Again, no physical object is moving at that speed. The spot is a pattern, the intersection of a light beam with a surface, and the pattern can propagate faster than any individual photon. These examples share a common feature. They involve the motion of patterns, intersections, or geometric features rather than the motion of matter, energy, or information. No signal can be sent using any of them. The scissors intersection cannot carry a message from one end to the other faster than sound traveling through the blade material. The spotlight spot cannot communicate between 2 points on the wall faster than light could travel directly between them. They are real faster-than-light phenomena in a precise technical sense, and they violate no laws of physics precisely because they involve no physical substance. The mathematical precision of the scissors example deserves elaboration. Consider a pair of scissors with blades each 1 million kilometers long. The pivot is at one end and you close the scissors by applying a force to the far end of one blade. The mechanical rigidity signal that closes the scissors travels through the metal at the speed of sound in the blade material, roughly 5 kilometers per second. But if we idealize the blades as perfectly rigid, the intersection point moves across the full length of the blade in the time it takes the far end to move by the blade separation at that point. For very nearly parallel blades of this length being closed even slowly, the intersection can move at arbitrarily high speeds along the blades. In practice, there is no such thing as a perfectly rigid body. Any force applied to one end of a real object transmits through the object at the speed of sound in the material, which is always far below c. This is a constraint from special relativity. The existence of a maximum propagation speed prevents any object from being truly rigid, because true rigidity would mean that a force applied at one end produces an instantaneous response at the other end, which would be faster than light signaling. Special relativity therefore predicts that all materials must be compressible to some degree, and this prediction is confirmed by the fact that no perfectly rigid material has ever been observed. The quantum eraser experiment provides another subtle case worth mentioning. In this experiment, measurements on one half of an entangled pair can retroactively affect whether interference patterns appear in the other half's detection record, but only after the two detection records are compared through a classical channel. Before comparison, neither record shows anything unusual. The information about which kind of measurement was performed on one half is not available in the other half's record alone. The quantum eraser thus appears to show a kind of retrocausal influence, but actually demonstrates once again that no information is transmitted faster than light. The apparent retrocausality only becomes visible through a classical comparison. In vacuum, nothing moves faster than light. But light in vacuum is already the theoretical maximum. In any medium, including air, water, or glass, light moves slower than c by a factor called the refractive index. Air has a refractive index slightly above 1, meaning light moves through it at approximately 99.97% of c. Water has a refractive index of about 1.33, meaning light moves through it at about 75% of c. Dense glass can have a refractive index of 1.5 to 1.9, meaning light travels through it at 53 to 67% of c. This reduced speed of light in media creates an interesting opportunity. A charged particle moving through a medium can move faster than light moves in that same medium. The particle is not breaking any universal speed limit. It is moving slower than c in vacuum. But it is moving faster than the local speed of light in the specific medium it inhabits. This situation, discovered theoretically by Pavel Cherenkov in the 1930s and explained theoretically by Igor Tamm and Ilya Frank, produces a distinctive radiation called Cherenkov radiation. Cherenkov radiation is the optical analog of a sonic boom. When an aircraft moves faster than the speed of sound, the pressure waves it creates cannot propagate ahead of it and instead pile up into a conical shock wave. When a charged particle moves faster than the local speed of light in a medium, the electromagnetic disturbances it creates cannot propagate ahead of it and instead build up into a coherent cone of light emission. The angle of this cone depends on the ratio of the particle's velocity to the speed of light in the medium. Cherenkov radiation is visible as a blue glow in nuclear reactors where radioactive decay products, primarily electrons, move through cooling water at speeds exceeding the local speed of light in water. The distinctive blue glow from reactor pools is one of the most visually striking manifestations of relativistic physics in an everyday setting. It is used extensively in particle physics detectors. Measuring the angle of Cherenkov light cones in detectors filled with water or transparent plastic allows precise measurement of particle velocities. In cosmic ray physics, Cherenkov radiation in the atmosphere is used to detect the highest energy cosmic ray events. When an ultra-high-energy proton or nucleus enters Earth's atmosphere, it creates an extensive air shower of secondary particles moving slightly faster than light in air, and these particles emit Cherenkov radiation as a brief flash of blue-white light. Telescope arrays like MAGIC and CTA in the Canary Islands are specifically designed to detect these nanosecond flashes of atmospheric Cherenkov radiation and reconstruct the energies and directions of the primary cosmic ray particles that produce them. The calculation of Cherenkov radiation angle provides a useful diagnostic tool in particle physics. The angle between the Cherenkov light cone and the particle's direction of travel is given by the cosine of the angle equals the speed of light in the medium divided by the particle's speed. For a particle moving at exactly the speed of light in the medium, the angle is 0 and the radiation is emitted directly forward. For faster particles, the angle is larger. By measuring the Cherenkov angle precisely, the particle's velocity can be determined with high accuracy, and combined with a measurement of momentum from the particle's curvature in a magnetic field, the particle's mass can be inferred. Ring imaging Cherenkov detectors, called rich detectors, are standard components in many particle physics experiments and in large neutrino detectors. In rich detectors, the Cherenkov photons are detected on a ring whose radius corresponds to the Cherenkov angle, allowing velocity measurements of individual charged particles. The IceCube Neutrino Observatory at the South Pole uses the ice sheet itself as the Cherenkov medium. High-energy neutrinos interact in the ice and produce charged particles that move faster than light in ice, emitting Cherenkov light that is detected by photomultiplier tubes embedded in the ice at depths of 1 to 2 kilometers. The direction and energy of the neutrinos are inferred from the pattern of Cherenkov light rings. Quantum entanglement is the phenomenon in which two particles can be prepared in a joint quantum state such that measurements on the two particles show stronger correlations than any classical theory would predict. When you measure a property of one entangled particle, the result you get is correlated with the result you will get measuring the other particle, even if the particles are separated by arbitrarily large distances. Einstein famously called this spooky action at a distance and found it deeply troubling, partly because it seemed to suggest some kind of instant influence across space. The correlations in quantum entanglement are genuine and have been experimentally demonstrated beyond any reasonable doubt. The experiments of John Bell in the 1960s, confirmed experimentally by John Clauser, Alain Aspect, Anton Zeilinger, and others over the following decades, showed that the correlations between entangled particles violate Bell's inequalities, proving that they cannot be explained by any theory of pre-existing hidden variables that travel with the particles. Something genuinely non-classical is going on. The Nobel Prize in Physics in 2022 was awarded to Aspect, Clauser, and Zeilinger for this work. But the correlations cannot be used to send information faster than light, and this is not a practical limitation but a fundamental one. Here is why. When you measure one entangled particle, you get a random outcome, such as spin up or spin down. The result is genuinely random. You cannot choose what result you will get. When your distant partner measures the other particle, they also get a random result. When you later compare results through a classical communication channel, you discover that the results were correlated. But neither party, during the measurements themselves, has any way to distinguish their results from random noise. To send information faster than light via entanglement, you would need to be able to control the outcome of your measurement, so that you could encode a message in the sequence of up and down results your partner observes. But you cannot control the outcome. The randomness of quantum measurement outcomes is not a practical limitation. It is a fundamental feature of quantum mechanics. There is no way to use entanglement to signal anything faster than light. The no-communication theorem, proven rigorously within quantum mechanics, ensures this. The experimental history of testing quantum entanglement has been extraordinarily productive in establishing both the genuine nature of the correlations and the impossibility of using them for faster-than-light signaling. The Bell inequality tests, from Clauser's original experiment in 1972 through Aspect's landmark experiments in the early 1980s and through the loophole-free experiments by multiple groups in 2015, have systematically closed the various theoretical loopholes that might have allowed local hidden variable explanations of the correlations. The 2015 experiments, including a landmark experiment at Delft University by Henson and colleagues, simultaneously closed the locality loophole, the detection loophole, and the freedom of choice loophole. The locality loophole requires that the measurements on the two entangled particles be made in a time interval short enough that no light speed signal from one measurement site could influence the other before it is complete. The Delft experiment separated the two entangled particles by 1.3 kilometers and made the measurements in a sufficiently short time that no causal influence could have connected them. The results confirmed quantum mechanical predictions and violated Bell's inequality, establishing the non-local character of the correlations beyond doubt. But at no point could any information be extracted from these correlations at either site without the classical channel comparing the results. The specific quantum mechanical feature that prevents using entanglement for signaling is the no-cloning theorem, which prohibits copying an unknown quantum state. If you could clone the state of your entangled particle, you could make many copies, measure them, and build up statistics that might reveal the state the distant partner had collapsed to. But quantum mechanics prohibits cloning, and this prohibition is directly linked to the linearity of quantum mechanics rather than being an ad hoc addition. Electromagnetic waves have two distinct velocities: phase velocity and group velocity. The phase velocity is the speed at which a fixed phase point in the wave, for example a peak or a trough, propagates through space. The group velocity is the speed at which a modulation or envelope of a wave packet propagates, and it is the group velocity that carries energy and information. The distinction matters because phase velocity can exceed the speed of light while group velocity cannot. In certain dispersive media, including plasmas and photonic crystals, the relationship between frequency and wavelength is such that phase velocity exceeds c. Experiments have demonstrated this directly. In 2000, Li-Jun Wang and colleagues at Princeton famously published results showing light pulses appearing to travel at 310 times the speed of light through cesium vapor. The results were genuine and caused significant media attention, with headlines proclaiming that Einstein's speed limit had been broken. The effect was real, but not what the headlines suggested. What was traveling faster than c was the peak of a pulse of light, a phase feature, not a signal. The cesium atom's response to the incoming pulse involved gain peaks at specific frequencies that constructively interfere to produce the outgoing pulse peak before the incoming pulse peak had even fully entered the medium. This is possible because of the way the medium reshapes the frequency components of the pulse. The mathematics is well defined and no information travels faster than c. To send information, you would need to send the leading edge of a signal, and the leading edge, the strict onset of a new signal that was not predictable from prior signal behavior, always travels at most at c. The formal statement is that the signal velocity, the speed at which genuinely new information propagates, is always at most c, regardless of what phase velocity or group velocity do. In anomalous dispersion media where group velocity exceeds c or even becomes negative, meaning pulses appear to exit before they enter, the signal velocity remains at most c. This is confirmed by the causal structure of the optical response, which is governed by the Kramers-Kronig relations and ultimately by the requirement of causality itself. The precise statement of what the Wang experiment demonstrated is instructive. The experiment used a narrow gain feature in the cesium absorption spectrum, and when the pulse entered this medium, the medium's spectral response reshaped the pulse so that the outgoing pulse peak appeared slightly before the incoming pulse peak had fully traversed the medium. This is allowed by classical electromagnetic theory without any violation of causality because the outgoing pulse peak is constructed from the spectral components already present in the leading tail of the incoming pulse. No new information is added. The medium is in effect predicting the peak position from the early tail of the pulse. To actually send information faster than c through this or any other anomalous dispersion medium, you would need to send something that could not be predicted from the prior temporal behavior of the signal. The strict onset of a new signal, sometimes called the wavefront, always travels at most at c even in anomalous dispersion media. This was proven mathematically by Sommerfeld and Brillouin in the early 20th century and confirmed by subsequent experiments. The signal velocity, the speed of the wavefront, is always at most c, regardless of the phase or group velocity. The Wang experiment confirmed this in a dramatic way that was initially misreported as a violation of the speed limit, but that on careful analysis turned out to be consistent with it. The broader point is that the examples of apparent faster-than-light propagation in optics and wave physics consistently turn out, on careful analysis, to involve the propagation of features rather than the propagation of new information. A feature is any aspect of a wave that can be predicted from earlier measurements of the wave. New information, by definition, cannot be predicted from earlier measurements. The distinction is precise and important, and in every case examined, new information propagates at most at c. The word tachyon comes from the Greek word for swift, and tachyons are hypothetical particles that would always travel faster than light. They are not ordinary massive particles accelerated beyond c. They are particles postulated to be born with imaginary rest mass, a quantity whose square is negative. This might sound like pure mathematical fiction, but the concept has been seriously explored within the framework of special relativity, and tachyons would have properties that are strange rather than merely impossible. The Lorentz factor for a tachyon with imaginary mass would be an imaginary number, but the product of imaginary mass and imaginary Lorentz factor produces a real momentum and real energy. A tachyon's energy decreases as its speed increases and approaches zero as the speed approaches infinity. The minimum energy of a tachyon is at infinite speed. Adding energy to a tachyon slows it down towards c. This is exactly backwards from ordinary matter, for which minimum energy is at rest and adding energy increases speed towards c. A tachyon traveling at exactly infinite speed would have zero energy and zero momentum, which is a physically unusual but mathematically definable state. Below infinite speed, tachyons have positive finite energy. The characteristic constant for a tachyon is the speed c, approached from above. Tachyons always travel faster than c and cannot slow to it, just as ordinary massive particles always travel slower than c and cannot speed to it. The most significant problem with tachyons is not that they require imaginary mass, unusual as that is, but that they would allow information to be transmitted backward in time. As we will explore in the causality chapter, in certain reference frames a tachyon carrying information from event A to event B would arrive at B before it left A in the time ordering of those events. A pair of observers using tachyon communicators could, in principle, arrange to send messages backward in time in their respective reference frames, creating causal paradoxes. Tachyons appear in modern theoretical physics in a different context from the naive faster-than-light particle. In quantum field theory and string theory, a tachyonic field is a field whose mass squared is negative at a particular point in field space, indicating that the point is a local maximum of the potential energy rather than a minimum. This signals an instability. The field will roll away from that point toward a true minimum. The Higgs mechanism involves a tachyonic field at the origin of field space, and the spontaneous symmetry breaking that gives particles their masses is the tachyonic field rolling to a lower energy minimum. The status of tachyons in current physics is largely as a theoretical construct with specific uses in quantum field theory rather than as a proposed explanation for any observed phenomenon. The tachyonic field that appears in the Higgs mechanism is a mathematical description of an unstable vacuum state. The field has negative mass squared at the origin, signaling that the vacuum is unstable and will spontaneously break symmetry to settle into a lower energy configuration. This is called a tachyonic instability, and it is a crucial mechanism in the standard model of particle physics, but the Higgs tachyonic field does not produce particles that travel faster than light. It is an instability in the vacuum, not a physical particle moving superluminally. In string theory, tachyonic fields appear in various contexts, including the bosonic string theory and certain unstable d-brane configurations. The tachyonic instability signals that the configuration being described is not the true vacuum, and the dynamics drives the system toward a stable lower energy state through what is called tachyon condensation. The mathematics of tachyon condensation in string theory has been studied extensively by Ashok Sen and others, revealing interesting structural properties of the string vacuum landscape. The search for free tachyon particles, those moving faster than light in the naive sense, has been conducted primarily through measurements of the neutrino rest mass. If neutrinos had imaginary mass, they would be tachyonic and would travel faster than light. Neutrino mass measurements from beta decay experiments, from cosmological constraints on the sum of neutrino masses, and from the observation of neutrinos from supernova 1987A, which arrived within the expected time window for massless particles, all confirm that neutrinos have small but real positive masses. They are not tachyons. In 1994, the Mexican physicist Miguel Alcubierre published a paper in the journal Classical and Quantum Gravity that described a solution to the Einstein field equations in which a spacecraft could travel at arbitrarily high apparent speeds without violating special relativity. The solution did not involve any massive object exceeding the local speed of light. Instead, it involved contracting the spacetime ahead of the spacecraft and expanding it behind, so that the spacecraft was effectively carried forward by the motion of the space around it rather than by any propulsion in the conventional sense. The Alcubierre metric describes a region of flat spacetime inside a bubble that moves through a region of spacetime that is curved by the required mass-energy distribution. The bubble itself moves faster than light relative to distant observers, and the spacecraft inside the bubble travels at speeds that could in principle approach any multiple of c with respect to distant observers. But at every local point within the bubble, the spacecraft is at rest relative to the local spacetime, and locally, the speed of light is the same as always. Special relativity is satisfied everywhere locally, but the global topology of the solution allows effective faster-than-light travel. The paper was met with serious scientific attention because it appeared to be a genuine solution to the equations of general relativity. The implications, if the solution could be realized, would be extraordinary. Interstellar travel on human timescales, exploration of the galaxy, potentially even intergalactic reaches. The solution was mathematically elegant and raised profound questions about what the light barrier actually forbids. The problems with the Alcubierre drive are numerous and severe, but the most fundamental is the energy requirement, which we will address in the next chapter. There are also serious questions about causality and controllability. The bubble, once moving faster than light, would be causally disconnected from any signals from outside it, meaning the pilot inside cannot steer the bubble because no information from the destination can reach them. Setting up the bubble in the first place would require manipulating space in a region where the spacecraft has not yet arrived, which seems to require solving the causality problem before you start. The Alcubierre paper sparked a significant body of follow-up work that examined the properties of the metric in detail and identified numerous practical and fundamental problems beyond the energy requirement. One significant issue is that an observer inside the warp bubble is causally disconnected from the bubble wall. Light from inside the bubble cannot reach the front wall because the bubble is moving faster than light. This means that no signal from the occupants can control or modify the bubble from the inside. The bubble must be set up and guided entirely from the outside, by observers who have a completely different reference frame and who must navigate without being able to see where the bubble is going in real time. Another concern involves the radiation environment inside the bubble. Quantum field theory calculations performed in the Alcubierre spacetime metric show that the quantum vacuum state produces significant particle creation inside the bubble, analogous to Hawking radiation from black hole horizons. The temperature and flux of this Unruh-like radiation increases with the speed of the bubble and could in principle be lethal to occupants for the kinds of faster-than-light velocities that would make interstellar travel interesting. The metric also requires that the exotic matter creating the curvature be arranged in a specific, detailed spatial distribution that changes with time as the bubble moves. Maintaining this distribution for a moving bubble while the occupants inside cannot communicate with the walls, and while quantum radiation is destroying the occupants, creates a fundamentally unworkable engineering scenario, even setting aside the energy question entirely. When physicists examined the Alcubierre metric carefully and calculated what it would require in terms of matter and energy to create and maintain the required spacetime curvature, the answer was dramatic. The original estimate by Alcubierre himself suggested that creating the bubble would require negative energy roughly equivalent in magnitude to the total mass energy of the planet Jupiter. This is already far beyond any foreseeable technology. But the situation is worse than that. The requirement is not merely for vast energy but for negative energy density, a quantity that violates what is called the weak energy condition. The requirement that the energy density be non-negative everywhere. General relativity places no mathematical prohibition on negative energy density, but quantum field theory suggests that negative energy densities, while possible in principle through the Casimir effect and related phenomena, are subject to quantum inequalities that severely limit how much negative energy can exist in any region for any length of time. The Casimir effect, in which two closely spaced conducting plates attract each other due to quantum vacuum fluctuations, does produce measurable negative energy density in the space between the plates. The effect is real and has been measured with great precision. But the total negative energy available is tiny. For plates separated by 1 nanometer, the negative energy density is of order -10 joules per cubic meter, immeasurably small compared to the requirements of a warp bubble. Harold White at NASA's Johnson Space Center proposed in 2011 that oscillating the bubble thickness could dramatically reduce the energy requirement, potentially to amounts of negative energy equivalent only to the mass of the Voyager spacecraft. This was widely reported but has not been accepted by the broader physics community as a reliable calculation, and subsequent analyses have not confirmed the reduction. The fundamental problem is that any configuration of spacetime geometry capable of enabling faster-than-light travel appears to require either exotic matter with negative energy density or the use of quantum gravity effects not described by any current theory. The Alcubierre drive is not ruled out by any direct physical prohibition, but it is not realizable with any known or theoretically plausible form of matter or energy. The quantum inequality framework provides the most fundamental constraint on negative energy densities. Ford and Roman derived in the 1990s that any spatial distribution of negative energy must satisfy an integral constraint. The magnitude of the negative energy multiplied by the squared inverse duration of its existence in any frame is bounded above by a quantity involving Planck's constant. The more concentrated the negative energy in time or space, the smaller its total allowed magnitude. This means that large, sustained, spatially distributed negative energy configurations of the kind required by the Alcubierre metric are essentially impossible given quantum mechanics. Physical derivations of the quantum inequalities trace them to the uncertainty principle applied to energy. Quantum mechanics does not permit a field to have a precisely defined energy below the vacuum value for arbitrarily long times. The Casimir effect, while producing genuine negative energy density between parallel plates, satisfies the quantum inequalities precisely because the geometry of the plates constrains how much negative energy can exist. The Alcubierre bubble requires negative energy far exceeding what the quantum inequalities permit over any macroscopic region. Van den Broek's modification of the Alcubierre metric in 1999 proposed making the interior of the bubble much larger than its exterior through a topology trick, reducing the energy requirement dramatically. While this modification does reduce the energy in some calculations, it introduces additional geometric complexity, and the modified metric still requires negative energy in amounts that violate the quantum inequalities, though by smaller factors. The fundamental problem remains that quantum mechanics appears to prohibit the kind of exotic matter distribution that any warp drive geometry requires. A wormhole is a hypothetical tunnel through spacetime connecting two distant regions. The concept has been part of theoretical physics since Einstein and Rosen described what are now called Einstein-Rosen bridges in 1935 as part of the mathematics of the Schwarzschild solution for black holes. The original Einstein-Rosen bridge connects two separate regions of an eternal black hole solution and is not traversable. Anything entering it is swept to the singularity before crossing to the other side. Traversable wormholes, which would allow passage from one region of spacetime to another, were studied theoretically by Kip Thorne and colleagues in the late 1980s following a suggestion by Carl Sagan, who wanted a physically plausible mechanism for faster-than-light travel for his novel Contact. The Thorne-Morris wormhole is a solution to the Einstein field equations that describes a tunnel through spacetime whose geometry is held open by exotic matter with negative energy density concentrated at the throat of the wormhole. The negative energy requirement for traversable wormholes is even more severe than for the Alcubierre drive. The exotic matter must be distributed at the wormhole throat with a specific negative energy density, and the requirement does not appear to be satisfiable by any quantum effect currently understood. The Casimir effect, mentioned in the previous chapter, produces negative energy but in amounts many orders of magnitude too small and in geometries that cannot be deployed in the cylindrical shape required by the wormhole throat. The quantum stability of wormholes is also problematic. When quantum fields are propagated through a wormhole solution, the vacuum fluctuations of those fields tend to produce runaway energy densities at the wormhole throat on infinitely short timescales, suggesting that quantum effects would destroy the wormhole before any signal or object could traverse it. This is not a definitive proof of impossibility, since it depends on approximations that break down near the Planck scale, but it suggests that quantum gravity effects would play a dominant role and that the wormhole as a macroscopic traversable structure is at best a quantum gravity problem rather than a classical general relativity one. The construction of a traversable wormhole, even if the exotic matter problem could be solved, raises additional fundamental issues. The topology of a traversable wormhole requires a connection between two distant regions of spacetime that is distinct from any path through normal space. Creating such a topological feature would, in most theoretical frameworks, require modifying the global topology of spacetime, not merely curving an already existing spacetime. General relativity describes how matter curves spacetime but does not naturally provide a mechanism for changing its topology. Whether topology change is possible in general relativity is an open question that likely requires a quantum gravity theory for its resolution. Thorne and his collaborators noted in their original wormhole work that if traversable wormholes exist, they could be used as time machines by moving one end of the wormhole at relativistic speeds, which would cause the two ends to become desynchronized in time. Returning something through the wormhole could then put it into the past of the original starting location. This connection between traversable wormholes and time travel is another manifestation of the causality argument that FTL shortcuts are equivalent to time machines. It suggests that the physical principles preventing time travel might also prevent traversable wormholes, even if the geometry is formally consistent with general relativity. The chronology protection conjecture, proposed by Stephen Hawking in 1992, formalizes this idea. Hawking conjectured that the laws of physics prevent the creation of closed time-like curves, paths through spacetime that loop back on themselves and could in principle be traversed to return to the past. He argued, based on quantum vacuum energy calculations, that quantum effects would always produce a diverging energy density at any prospective closed time-like curve horizon, destroying the spacetime structure before the time loop could form. This conjecture has not been proven in full generality but is supported by calculations in specific spacetime geometries. One of the most remarkable features of modern cosmology is that the expansion of the universe routinely carries objects away from each other at speeds exceeding the speed of light. This is not a theoretical speculation or an extreme edge case. It is the everyday reality of cosmology for sufficiently distant objects, and it has been true since very early in cosmic history. The Hubble constant, currently measured at approximately 67 to 73 kilometers per second per megaparsec depending on the method used, means that for every megaparsec of additional distance, the recessional velocity of a galaxy increases by this amount. 1 megaparsec is approximately 3.26 million light-years. The Hubble radius, the distance at which recessional velocity equals the speed of light, is currently about 14.4 billion light-years, or about 4,400 megaparsecs. Galaxies beyond this distance are receding from Earth faster than c. This is not a violation of special relativity, which applies to motion through space. The recessional velocities are not motion through space in the relevant sense. They arise from the expansion of space itself. The distinction can be made precise in general relativity. Locally, at any given point in space, the speed of any object relative to the local expansion frame is always less than c. It is the cumulative effect of this local expansion over cosmological distances that produces apparent recessional velocities exceeding c. The observational consequence is that light emitted by galaxies beyond the Hubble radius is not necessarily lost to us. Even though such galaxies are currently receding faster than c, light they emitted in the past, when they were closer, is already in transit toward us and will eventually arrive. What we cannot receive is light emitted now from beyond the Hubble radius. That light, even at c, cannot overcome the expansion of the intervening space. The particle horizon, the boundary of the observable universe, is at approximately 46 billion light-years, and we can see objects up to that distance, even though those objects are now receding far faster than c. The precise formulation of why Hubble recession velocities can exceed c without violating special relativity involves understanding that special relativity applies in flat spacetime and in local frames. General relativity, which describes curved spacetime including the expanding universe, does not globally restrict recession velocities to c. The Hubble recession velocity is defined as the rate of change of proper distance, the physical distance between 2 points measured along a surface of constant cosmic time. This is a coordinate velocity defined in a specific way in the cosmological framework, and it can exceed c for sufficiently distant objects. What special relativity does restrict is the velocity of any object relative to a local inertial frame. This velocity is always less than c. For objects beyond the Hubble radius, their local velocity relative to any locally defined inertial frame is still less than c. The superluminal recession is a global effect of the metric, not a local violation of the speed limit. The distinction matters because it is the local speed limit that prevents causality violations. The global recession velocity in an expanding universe does not create causal paradoxes. The fact that we can observe galaxies currently receding faster than c through telescopes like the Hubble Space Telescope and the James Webb Space Telescope sometimes causes confusion. How can we see something that is moving away from us faster than the light it emits? The answer is that the light we receive now was emitted in the past, when the galaxy was closer and its recession velocity was smaller, and the light has been in transit through expanding space ever since, making progress toward us even as the space behind it expanded. Whether the photon makes net progress toward us depends on whether the recession velocity is less than c at the photon's current location, and during much of the photon's journey the recession velocity at its location was less than c, allowing it to reach us. The accelerating expansion of the universe means that the Hubble constant is not actually constant over time, despite its name. Its value changes as the universe evolves, and the current value of approximately 67 to 73 km per second per mpc represents its value at the current cosmic epoch. In the far future, as matter density dilutes and dark energy comes to dominate completely, the expansion rate will approach a constant asymptotic value determined by the cosmological constant. The Hubble radius will then stop growing and fix at a specific size, after which no new information from beyond that boundary can ever reach us, making the event horizon and the Hubble radius coincide in the asymptotic de Sitter state. Cosmic inflation is the theoretical framework proposing that in the universe's first approximately 10 to the minus 32 seconds, space underwent an exponential expansion that increased the scale of the universe by at least a factor of 10 to the 26 and possibly by many orders of magnitude more. During inflation, any 2 points that were adjacent before inflation were separated to distances far exceeding the Hubble radius in a time incomparably shorter than the Planck time. The expansion rate was incomprehensibly faster than the current Hubble expansion, which is itself already producing recessional velocities exceeding c for distant galaxies. Inflation was proposed by Alan Guth in 1980 to explain 3 observational puzzles about the universe: the horizon problem, the flatness problem, and the magnetic monopole problem. The horizon problem is the fact that the cosmic microwave background has the same temperature to 1 part in 100,000 in all directions, even between regions of the sky that are space-like separated, meaning that no causal influence could have connected them after the Big Bang without inflation. Inflation solves this by proposing that these regions were in causal contact before inflation began and were then driven apart by the inflationary expansion to distances where causal contact was impossible. The expansion during inflation was not the motion of any object. It was the expansion of the metric, the geometry of spacetime itself. Nothing moved faster than light through space. It was the space between points that was expanding faster than light. This is precisely the same mechanism that causes present-day Hubble recessional velocities to exceed c for distant galaxies, but operating at a rate perhaps 55 orders of magnitude faster. Inflation thus represents a period when the universe was already doing, at extraordinary rates, what it continues to do today at much more modest rates. The inflationary expansion set the initial conditions for all subsequent cosmic evolution, explaining the remarkable large-scale uniformity and flatness of the observable universe. It also amplified quantum fluctuations in the inflaton field to macroscopic scales, providing the seed perturbations from which all cosmic structure, galaxies, clusters, the cosmic web, eventually grew. The specific predictions of inflation that have been confirmed observationally are worth enumerating because they transform inflation from a speculative hypothesis into a well-supported physical theory. The flatness of the universe, measured precisely through the angular power spectrum of the cosmic microwave background temperature fluctuations, is consistent with inflation's prediction of a total density extremely close to the critical density. The CMB temperature uniformity, at 1 part in 100,000 across the full sky, including regions that were causally disconnected after the Big Bang without inflation, is naturally explained by inflation. The absence of magnetic monopoles, which would have been created at high abundance in the hot early universe and would have dominated the current energy density, is explained by the dilution of their number density by the inflationary expansion. The most specific observational prediction of inflation is the spectrum of primordial density perturbations that seeded galaxy formation. Inflation predicts a nearly scale-invariant spectrum of perturbations, with a slight tilt toward larger power at larger scales, and a specific ratio between scalar and tensor perturbations. The scalar perturbations correspond to density fluctuations in the inflaton field. The tensor perturbations correspond to gravitational waves produced by quantum fluctuations during inflation. The Planck satellite measurement of the CMB power spectrum confirmed the scalar spectral index at 0.968 plus or minus 0.006, consistent with inflationary models. The tensor-to-scalar ratio has not been detected, placing an upper bound that rules out some inflationary models while allowing others. The search for primordial gravitational waves from inflation in the polarization of the cosmic microwave background, specifically the B-mode polarization signal, is one of the primary goals of current and next-generation CMB experiments, including BICEP, the South Pole Observatory, and the Simons Observatory. The accelerating expansion of the universe, driven by dark energy, creates a specific type of horizon called the cosmological event horizon. Unlike the particle horizon, which marks the edge of the region from which light has had time to reach us since the Big Bang, the event horizon marks the edge of the region from which any signal emitted today can ever reach us in the future. The event horizon is currently at approximately 16 billion light-years. Any galaxy beyond 16 billion light-years that emits light today will never have that light reach us. The accelerating expansion will carry the intervening space away at an accelerating rate that will eventually outpace even light's ability to cross it. More distant galaxies are already beyond our event horizon and will never be observed regardless of how long we wait or how powerful our telescopes become. The universe contains information that is permanently and irreversibly beyond our reach. This means the observable universe is shrinking in a specific sense. While the particle horizon continues to grow, allowing us to see further back in time, the event horizon does not grow, and the portion of the current universe that we will ever be able to observe is finite and contracting relative to the total. In the far future, the only visible galaxies will be those gravitationally bound to our local group. All others will have been carried beyond the event horizon, their last signals arriving redshifted to invisibility. What lies beyond the event horizon is, in the most literal physical sense, unknowable from within our region. Whatever physics operates there, whatever events occur, whatever structures exist, produce no signal that will ever reach us. The event horizon is a causal boundary defined by the structure of an accelerating spacetime, an absolute limit on what any observer within our Hubble volume can ever know about the universe beyond it. This region beyond the event horizon contains, statistically, the same distribution of matter and structure as within it. There is no physical boundary there, no wall, no change in the laws of physics. The boundary is purely informational, defined by the propagation of light and the expansion of space. What lies past it is, to the highest precision physics allows, more universe, governed by the same laws, containing the same kinds of structures, producing the same physical processes, but permanently inaccessible from here. The thermodynamic properties of the cosmic event horizon have been studied in analogy with black hole horizons, and the connection is deep and mathematically precise. Just as a black hole horizon has a temperature proportional to the surface gravity at the horizon and an entropy proportional to the horizon area, the cosmic event horizon in de Sitter space, the solution to general relativity with a positive cosmological constant approximating the universe in the far future, has a temperature proportional to the Hubble constant and an entropy proportional to its area measured in Planck units. The temperature of the de Sitter horizon is approximately 10 to the minus 30 Kelvin, far colder than any physical system except the future universe itself. The finite entropy of the cosmic event horizon has a profound implication. A system with finite entropy has a finite number of distinguishable states, equal to 2 raised to the power of the entropy in bits. For a universe settling into a de Sitter state with finite event horizon area, the number of possible states of the observable universe is finite, and the universe would eventually explore all of them. Over an incomprehensibly long but finite time, every possible configuration of matter within the horizon would recur. This is a deep relativistic version of Boltzmann's Poincare recurrence, and illustrates how the thermodynamics of horizons is connected to the deepest questions about the long-term fate of the universe. The specific causal structure of the event horizon also determines what kinds of experiments can be performed within the observable universe. Any quantum information trapped beyond the horizon is irretrievably lost, and this loss is accompanied by an increase in the entropy of the observable region. The cosmic horizon is not merely a boundary of observation, but an active thermodynamic system participating in the entropy budget of the universe. The statement that faster-than-light communication would enable time travel is not a metaphor or a science fiction extrapolation. It is a straightforward consequence of special relativity, derivable through a specific construction that deserves to be laid out clearly. Consider two observers, Alice and Bob, in relative motion. Alice sends a tachyon signal to Bob at twice the speed of light in Alice's reference frame, and the signal reaches Bob at a time, in Alice's frame, later than it was sent. So far, no problem. The signal arrived after it was sent. But special relativity requires that we consider how this sequence of events looks in Bob's reference frame. Because Alice and Bob are in relative motion, and because the signal traveled faster than light, the Lorentz transformation of the events, Alice sending and Bob receiving, can produce a temporal ordering reversal. In Bob's frame, the reception event may precede the sending event. Bob received the signal before Alice sent it, in Bob's reference frame. Now Bob immediately sends a tachyon reply to Alice at twice the speed of light in Bob's frame. This reply, in Bob's frame, is sent after he received Alice's signal. But by the same Lorentz transformation argument applied to the second signal, in Alice's frame, the reply arrives before Alice sent the original signal. Alice has now received a reply to a message she has not yet sent. The logical paradoxes that follow from this, the grandfather paradox and its variations, are familiar from discussions of time travel. What is important here is that they are not merely paradoxes in the fictional sense. They represent genuine logical contradictions in the structure of physical theories that attempt to incorporate faster-than-light signaling. Any consistent theory that includes both special relativity and faster-than-light communication must either abandon one of them or impose a specific mechanism that prevents the paradoxes, such as the Novikov self-consistency principle. This connection between FTL communication and time travel is one of the strongest arguments that the light barrier, if it can be exceeded at all, cannot be used for signaling. The specific Alice-Bob argument deserves a numerical example to make the time travel conclusion concrete. Suppose Alice and Bob are separated by 100 light-seconds and Bob is moving toward Alice at half the speed of light. Alice sends a tachyon at 4 times the speed of light in her reference frame toward Bob. In Alice's frame, the signal travels 100 light-seconds at 4 times c and arrives at Bob in 25 seconds. So far nothing objectionable. The signal arrived 25 seconds after it was sent. Now compute the same events in Bob's reference frame. Bob's velocity relative to Alice is 0.5 c, giving a Lorentz factor of approximately 1.15. Using the Lorentz transformation, Bob calculates that the signal arrived at him before Alice sent it, specifically by approximately 2.9 seconds in his frame. The signal arrived at Bob before it was sent from Alice in Bob's reference frame. Bob immediately uses a tachyon transmitter to send a reply back to Alice at 4 times the speed of light in his reference frame. In Bob's frame, the reply is sent before Alice's original message was sent. Transforming back to Alice's frame, Alice receives the reply approximately 13.5 seconds before she sent her original message. She now knows the content of whatever Bob replied before she has sent anything. She can use this knowledge to decide whether to send the original message or what to put in it, creating the kind of causal loop that produces logical paradoxes. The conclusion is not just philosophical, it is mathematical and direct. The Novikov self-consistency principle, proposed as a way out of such paradoxes, asserts that only self-consistent histories are allowed. Under this principle, Alice's use of the advanced knowledge must always lead to her sending exactly the message that was consistent with Bob's reply. The universe would only allow causal loops if they were self-consistent. This resolves the logical paradox, but at the cost of eliminating any meaningful free choice for Alice, which many physicists find unsatisfying as a resolution. For most of the history of physics, the speed at which gravitational influence propagates was either assumed to be infinite, as in Newton's theory, or an open theoretical question. General relativity predicts that gravitational influences propagate at c, but testing this prediction requires observing a changing gravitational source and measuring how quickly its effects reach distant observers. The detection of gravitational waves from neutron star mergers provided the most direct test. The event GW170817 in August 2017 was detected by the LIGO-Virgo gravitational wave network and, 1.7 seconds later, by the Fermi Gamma-Ray Space Telescope as a short gamma-ray burst. The two signals traveled for approximately 130 million years from their source. If their speeds differed by even 1 part in 10 to the 15th, the time difference over that distance would have been far larger than 1.7 seconds. The 1.7-second difference is consistent with the expected physical delay between the neutron-star merger and the launching of the gamma-ray burst jet, meaning the gravitational waves and the light traveled at the same speed to within 1 part in 10 to the 15th. This measurement established that gravity propagates at the speed of light, or more precisely at c, to extraordinary precision. Any theory proposing that gravity is mediated by a massless spin-2 field, which is the description of gravitons in quantum field theory, automatically predicts propagation at c. The GW170817 measurement confirmed this to an accuracy that rules out most alternative gravity theories that propose different propagation speeds. The Newton's third law concern about the finite speed of gravity, that Earth should feel the Sun's gravity as it was 8 minutes ago rather than as it is now, and that the solar system should spiral outward as a result, is resolved in general relativity by the fact that for bodies moving at constant velocity, the leading order effect of the finite propagation speed is automatically compensated by terms in the equations that preserve energy and angular momentum. Radiation reaction, the energy lost to gravitational waves, does cause orbits to decay, as was demonstrated in the Hulse-Taylor binary pulsar system, but the rate is extremely small for typical solar system bodies. The historical puzzle about the speed of gravity, which seems at first to suggest that Newtonian instantaneous action at a distance could be correct given the stability of the solar system, was partially addressed by Laplace in the early 19th century. Laplace showed that if gravity propagated at a finite speed, orbiting bodies would experience a gravitational force not in the direction of the current position of the attractor but in the direction of its retarded position, the position it occupied a light travel time ago. This retardation would cause the force to be slightly behind the body's current motion direction, producing a torque that would cause orbits to spiral outward rapidly. Laplace calculated that if gravity propagated at a finite speed, the solar system stability required it to be at least 7 million times faster than light. This seemed to argue for infinite propagation speed. The resolution in general relativity involves the fact that for bodies moving at constant velocity, the leading order retardation effect is exactly cancelled by a velocity-dependent correction to the gravitational force, making the effective force point toward the current position of the source rather than its retarded position. This cancellation is exact for uniform motion and approximate for accelerated motion, with the remaining error corresponding to the emission of gravitational radiation that causes the orbit to decay. The same cancellation occurs in electromagnetism for charges moving at constant velocity, where the electric field of a uniformly moving charge points toward the charge's current position rather than its retarded position. This is the Lenard-Weichert potential result. The cancellation in both cases reflects the deep connection between Lorentz invariance and the specific form of the force law, and it is what allows planetary orbits to be stable despite the finite propagation speed of the gravitational interaction. The connection between the speed of light, information transmission, and the structure of physical theories is deeper than a simple speed limit. Shannon information theory, the mathematical framework describing how information can be encoded, transmitted, and decoded, has specific things to say about what it means to transmit information and what constraints any physical transmission must obey. The fundamental question is whether any of the faster-than-light phenomena described in previous chapters can be used to transmit information, to convey a message from a sender to a receiver that the receiver could not have predicted without receiving the transmission. The answer, in every case examined, is no. The mathematical proofs of this for quantum entanglement are particularly clean. The no-communication theorem shows that no sequence of local operations on one half of an entangled pair can be detected by measurements on the other half. The results at the other end are always consistent with a purely local description and carry no trace of what happened to the distant particle. Thermodynamics adds another dimension. The second law of thermodynamics connects information to entropy, and the connection between faster-than-light signaling and time travel has thermodynamic implications. A time machine would allow information to travel from the future to the past, which could in principle be used to reduce the entropy of a system, violating the second law. The prohibition on faster-than-light signaling, therefore, has a thermodynamic interpretation. It is part of the enforcement of the second law's statistical arrow of time. The holographic principle in theoretical physics, emerging from studies of black hole entropy by Stephen Hawking, Jacob Bekenstein, and later Gerard T. Hooft and Leonard Susskind, suggests that the information content of any region of space is bounded by its surface area divided by the Planck area. This bound, The Bekenstein-Hawking entropy formula connects spacetime geometry to information capacity in a fundamental way. The speed of light appears in the Planck units that define this bound, suggesting a deep connection between the light barrier and the maximum information density the universe allows. The black hole information paradox provides another angle on the connection between the speed of light and information. When matter falls into a black hole, classical general relativity says that the information about its quantum state is lost. The black hole is completely characterized by only three parameters: its mass, charge, and angular momentum, regardless of what kind of matter fell in. This apparent destruction of quantum information violates the unitarity of quantum mechanics, which requires that information is conserved. Hawking radiation, the quantum thermal emission from black holes predicted by Stephen Hawking in 1974, allows a black hole to eventually evaporate completely. The question is whether the information about the infalling matter is encoded in the Hawking radiation emitted over the black hole's lifetime. Hawking originally argued that it was not, that the radiation was truly thermal and contained no information about the infalling matter, implying a fundamental violation of quantum mechanics. This is the black hole information paradox. The current theoretical consensus, shaped by the argument from the unitarity of the full quantum theory, is that information must be preserved and must be encoded in the Hawking radiation, but the mechanism by which this happens is not well understood. The AD/CFT correspondence, a specific realization of the holographic principle in string theory, provides a mathematical framework where the information is demonstrably preserved in the radiation, but the detailed mechanism by which information escapes from inside the horizon without violating causality remains an active area of research. The light barrier and the causal structure of black hole horizons are central to this problem, which stands at the intersection of quantum mechanics, general relativity, and information theory. The honest answer to whether the speed of light is an absolute limit is probably yes, but we cannot be completely certain, and the specific ways physics could be wrong about it are interesting to examine. Special relativity has been tested with extraordinary precision. The Lorentz invariance, the symmetry that underlies the constancy of c, has been tested in countless experiments using atomic clocks, particle accelerators, cosmic ray measurements, gravitational wave detections, and astronomical observations. Violations at the levels tested are ruled out to precisions of 1 part in 10 to the 20 or better in some experiments. If the speed of light is not an absolute maximum, the violation is extremely small at energies currently accessible. Some quantum gravity theories, including certain versions of loop quantum gravity and some string theory scenarios, predict that Lorentz invariance might be violated at energies approaching the Planck scale, roughly 10 to the 28 electron volts. The particles produced in the most energetic cosmic ray events reach energies of approximately 10 to the 20 electron volts, about a factor of 10 million below the Planck scale. No Lorentz invariance violation has been detected in cosmic ray data, which places increasingly tight constraints on any such violation. The sensitivity has improved as the sample of detected ultra-high-energy cosmic rays has grown and as analysis methods have improved. The Planck scale cutoff is significant because it suggests that even if our current picture of the light barrier is approximate rather than exact, the corrections are inaccessible at any energy humanity has produced or can plausibly produce in the foreseeable future. LHC energies are roughly 10 to the 13th electron volts, 15 orders of magnitude below the Planck scale. Any Lorentz invariance violation would need to appear well below the Planck scale to be technologically relevant. The more optimistic version of the physics could be wrong argument notes that physics has been wrong about absolute limits before. Newton's mechanics was replaced by special relativity, which imposed new limits that Newton's mechanics did not. Perhaps some successor theory to special relativity and general relativity, perhaps a theory of quantum gravity, will reveal new structure at or above the apparent C limit that permits communication or travel of a new kind not contemplated in the current framework. This is possible but would require finding physical phenomena that current theories do not predict and that survive the extraordinarily precise tests that the current framework has passed. The history of Lorentz invariance tests is instructive about both the precision of current constraints and the specific forms of violation that have been searched for. The Standard Model extension, developed by Alan Kostelecki and colleagues, is a general theoretical framework that parameterizes all possible Lorentz invariating terms that could be added to the Standard Model. It provides a systematic language for testing Lorentz invariance across different sectors of physics. Measurements in particle physics, atomic physics, gravitational experiments, and astrophysical observations have been used to constrain the coefficients of these terms to extraordinary precision in each sector. The photon sector of the Standard Model extension tests whether different polarizations of light travel at different speeds, whether the vacuum is birefringent. Astrophysical measurements of polarized light from gamma-ray bursts have constrained differences in photon speed between polarizations to better than 1 part in 10 to the 38, 18 orders of magnitude more sensitive than the best laboratory measurements. These observations use the photon travel time over cosmological distances as a lever arm that amplifies any tiny speed difference to a detectable polarization rotation. The gravitino sector, testing whether the speed of gravitational waves equals c precisely, has been constrained by the GW 170817 measurement to 1 part in 10 to the 15th. The neutrino sector has been tested by the SN 1987A observation. Neutrinos and photons from the supernova arrived within seconds of each other after traveling 168,000 light-years, confirming that neutrinos and photons travel at the same speed to better than 1 part in 10 to the 10th, or more precisely placing the neutrino-photon speed difference at less than about 2 times 10 to the minus 10 times c. The light barrier is not a wall that the universe put up to frustrate physicists and science fiction writers. It is a feature of the universe's deepest architecture, connected to causality, thermodynamics, information theory, and the structure of spacetime in ways that appear on careful examination to be mutually reinforcing. The speed of light is the rate at which the universe allows causes to propagate. Everything else follows from that. What lies past the light barrier depends on what you mean by past. If you mean moving through space at speeds exceeding c, the answer is that no object with mass and no information-carrying signal has been observed to do this. The theoretical reasons for thinking it impossible are substantial and multiple, and the best proposals for circumventing the limit, warp drives and wormholes, require either negative energy in quantities that quantum mechanics seems to prohibit or other physics not yet known. The honest answer is that nothing we can observe or construct lies past the light barrier in this sense. If you mean phenomena whose behavior in some relevant quantity exceeds c, the universe is full of them. The expansion of space carries distant galaxies away faster than light. The inflationary epoch expanded the universe at rates incomparably faster. Phase velocities in dispersive media exceed c. Geometric features like scissors intersections and spotlight spots can move faster than c. None of these carry information. All are consistent with special relativity. All are in this sense already past the light barrier. They reveal that c is not the maximum speed of every phenomenon, but specifically the maximum speed of information and material objects through space. If you mean what physics might discover beyond the current understanding of the light barrier, the answer is that the history of physics gives reason for humility. Every confident boundary of knowledge has eventually proven more permeable than it seemed. The atom was indivisible until it wasn't. Newton's mechanics were universal until they weren't. The current understanding of c as an absolute maximum is the most precisely tested and most deeply embedded theoretical limit in physics. But it is not immune to revision by better theory or unexpected observation, and the specific ways it might be revised are worth studying precisely because they require understanding exactly what the current limit means, why it holds as well as it does, and where the first cracks might appear. The universe communicates with itself at the speed of light. Every causal influence, every signal, every force-carrying particle or field propagates at most at this rate. The universe we inhabit is shaped by this limit, from the structure of atoms through the behavior of galaxies to the causal architecture of spacetime itself. Understanding the light barrier is understanding the universe's operational speed, the rate at which reality updates itself, the fastest that here can know about there. Past it, in the strict causal sense, is beyond knowing, not because we lack the instruments, but because the universe itself has placed it outside the reach of any signal that could carry the news. There is a particularly human dimension to the desire to exceed the speed of light that deserves acknowledgement before closing. The stars are appallingly far away. The nearest star system to the Sun, Alpha Centauri, is 4.37 light-years distant. At any speed achievable with current or foreseeable propulsion, the journey would take generations. The galaxy, at 100,000 light-years in diameter, is effectively inaccessible on any human timescale without orders of magnitude improvement in speed beyond anything currently achieved. The emotional appeal of faster-than-light travel is therefore understandable and entirely honest. The universe has laid out an almost incomprehensible amount of structure, stars, worlds, complexity, and has simultaneously placed virtually all of it outside any reach we can currently contemplate. The stars visible in the night sky are not invitations. They are beautiful and permanent reminders that the universe's scale is indifferent to human timescales. Physics does not offer easy comfort here. The constraints are real, the alternatives are technically demanding at best and probably impossible at worst, and the universe does not adjust its speed limit for the aspirations of the organisms that discovered it. But the precision with which we understand the barrier, the depth at which it is embedded in the structure of causality and information and thermodynamics, and the ingenuity of the proposals that have been made to circumvent it are themselves remarkable achievements of the same intelligence that experiences the frustration. We discovered the barrier, mapped its mathematical structure, found all the loopholes and showed why they close, and continue to search for any departure from it that precision measurement might reveal. That is not nothing. The question of what lies past the light barrier remains one of the most consequential in all of physics, not because any known phenomenon is there, but because the answer determines what kind of universe we inhabit, how large our effective reach is, how alone we are in practice even if not in principle, and whether the universe's deepest rules as we currently understand them are complete or still hiding something.